She was like, literally, his recommendation.
I don't really care for the term switch gears, but let's use it anyway. We're going to switch gears
fell in love with you.
and talk about a different disorder that probably you've heard different aspects of it because it's pretty, it's in a lot of textbooks.
But yeah, he like wrote this
some
great
aspect of this, sickle cell.
Maybe it was really sweet. Like,
Anybody know what globin genes have to do? What are these little crazy red cells? Oh, look, some of them are funny
like in like my progression because he's
Oh,
like,
and there's some
you know.
blue
I was like, that's like a cool point.
What are those cells?
She loved it. So.
And diagnose the disease for me, just looking at these cells. What?
Yeah. So,
Who's? Yes. What does globin have to do with sickle cell?
He was really nice.
And which are the functioning cells here? Are these round
Everything
ones?
is like he's not a professor.
Or are these sickle
Yeah,
shaped
exactly.
ones?
Like I just showed her because it was like just like you didn't even have to have.
So yeah, that's what we
But I,
see in
I
the
was like,
blood.
He just
What
offers
is,
like a cool point of view.
what is
He seen me
globin?
progress from when I was shitty freshman year to like.
Carries oxygen.
And that's what I want.
Oxygen important?
That's what I need actually.
Is oxygen important for these cells? Or what's the main function of these cells carrying oxygen?
So you don't
It's transported from the lungs, picks up oxygen in the lungs and carries it to the peripheral tissues and dumps it off and then they go back. Anybody know what these? What are the blue things in there? Looks like there's 3 blue blobs inside this circle of pink. Anybody know what that is? What? White blood cell, yeah, I can't tell. That's probably a polymorphic PMNL. Polymorphonuclear lymphocyte. Yes. I'm not much of a gynecologist, so I'm just kind of guessing. But the vast majority of the cells in the blood, of course, are red blood cells by far. But there are scattered white cells in the tube doing different functions. Now, the thing I wanted to point out, we know that globin carries oxygen. Are all of the symptoms of sickle cell related to the decreased oxygen carrying capacity? This is something you might not necessarily. Why are you shaking your head now?
The sickle cell shape gets caught on each other and they cause blood clots.
Yeah, it's not so much in the major blood vessels, but there's a lot of what are collectively be called microvessels, micro blood vessels, really tiny little things in all of your tissues, right? Because you gotta get the oxygen into the cells in the interior of a big organ. Well, those microvascular, the micro blood vessels are so small that 1 or 2 of these abnormally shaped sickle cells can clot up. And that leads to, might be just a little cell death originally just in one place, but then there's another clot and another clot and another clot, and suddenly you've got massive cell death.
Which I never knew.
So that can be really devastating to go along with
They painted
the side effects or the bad effects of being anemia. Okay, so just to remind you, a lot of things I'm going to say initially probably you already know, but I do want to put this in a historic context because globin, in the study of globinopathies, is really historical significance to medical genetics for a number of reasons. It's the first, so the sickle cell disease was the first molecular disorder. It was the first identified to be a mutation that's affecting the structure. The structure of hemoglobin was the first protein structure to be solved by actually diffraction. That resulted in a Nobel Prize for Max Kaluza. Clinical significance? It's really striking. I mean, everybody's heard of sickle cell, right? And you're thinking, oh, well, that's mainly, affecting its high incidence. What part of the world is sickle cell at high incidence in? Africa. Everybody knows that the most, but it's really around the entire Mediterranean, close to the Mediterranean. Yeah. And the problem is, there's a couple problems, and we'll see the statistic in a few slides. The vast majority of the countries where sickle cell and related genetic disorders of beta globin, so there's other ones, and really not just sickle cell, their high incidence is in underdeveloped countries, poorer countries. Okay. Now, even in those poorer countries, there's better conditions for the kids that start showing clinical signs of sickle cell or the thalassemias that are related to blood disorders. So there's things that are going on, the overall nutrition in most of these underdeveloped countries is getting better, and there's a lot of treatment for some of the other problems that kids have, infectious diseases, and so on. The problem is then they're surviving. I mean, of course we would want them to survive, but that's affecting, think of this in a population sense, that's affecting the allele frequency. So there's a lot more kids that are surviving that have these mutations, which of course we want, but on the other hand, it's creating more of a global health burden. Okay. So we've got to fix that somehow. And yeah, you're thinking gene therapy. And I'll actually show you some examples at the end of these slides. Gene therapy for not correcting these mutations, but for greatly reducing the symptoms is really promising. In fact, there's a very successful, I'll show you the very last slide, I think. There's it appears to be a very successful clinical trial ongoing in Boston now at Children's Hospital for gene therapy that has been outstandingly good with this guy that has sickle cell. Problem is, gene therapy is really, really, really expensive. Are you going to be able to use gene therapy in these really poor countries? No. Probably not unless the Gates Foundation kicks in a lot of money, right? So people are actively looking for cheaper and effective alternatives to gene therapy, like small molecules, and that's where this paper comes in. It's one example. The design paper is one example of trying to find something else. It's going to target the same protein that's involved, that's been successful with the gene therapies. It's not globin itself. It's a gene that regulates globin expression. Doesn't regulate all globin gene expressions. We'll just see, we'll see. Okay, population genetics and allele frequency. Evolutionary, I'll show you a little bit about that. Developmental and complex, I'll just show you a little tidbits of this. Not population genetics, you already know about that, and we discussed it briefly. What about the evolutionary stuff? So just to remind you, here's our hemoglobin. Carries heme groups. Each heme group can have an oxygen. So each hemoglobin can carry 8 oxygen, 4 O2s. Okay? Now, the important thing here, and this is important to understanding how both the diseases and the therapy could work. Each hemoglobin, not only does it have 4 heme groups, but there's actually a tetramer. 2 what are called beta chains and 2 alpha chains. They're structurally related. In fact, that's the evolutionary interest in them. They arose, this is a multi-gene family that arose from a lot of genomic studies, gene duplication, and they know they can follow the evolutionary tracing of it. So, I said with each hemoglobin, there's 2 beta globins and there's 2 alpha globins. Well, the globin clusters, there's one on chromosome 11. You don't have to know that it's chromosome 11. But on linked to that is another cluster. The one on chromosome 11 are the beta globin-like genes. So there's a whole family, 1, 2, 3, 4, 5 different beta globin genes. Each of these colored genes expresses a beta globin. There's 1, 2, 3, 4, 5 different alpha globin genes. Anybody know why? Oh, did I miscount these 6 up here? we've got 1, 2, 3, 4, 5. What's this one? This is epsilon, this is gamma, delta, beta. What's that funny symbol? Anybody know? There's 2 of them here. I think I heard something.
Psi.
Yeah. What is the why would that be labeled? It looks like that's a gene, right? If these rectangles, colored ones are genes, what would a label of psi on what appears to be a gene be indicating? And why would I exclude this one from saying, when I said there were 5 beta globin-like genes in that cluster? Anybody ever heard of genes that get inactivated during evolution? You just accumulate random mutations and they get inactivated. They're no longer functioning genes. You can still identify them. Pseudogenes, yes. So that psi symbol is what's often used. So there's 2 pseudogenes in the alpha gene cluster. 1 pseudogene. So they were at one point functioning genes, but there's no selection. All of these, so both there was a common ancestral gene to the beta globin cluster and to the alpha globin cluster, but then within each cluster there are multiple rounds of gene duplication. So this is a classic case of evolution through both genome-wide duplication and gene duplication. What are these called? Homolog is the general term. So the epsilon gene is homologous to the beta globin gene, which is homologous to the alpha 2 globin gene. But what's the term for when you have homologous genes within the same species that have a common ancestor? Paralogs. Yes, so this is the classic case of evolution of paralogous genes. But it's also a great case of evolution of orthologous genes too, because there's this gene family is present in every vertebrate. And there's some really cool, interesting stuff. In fact, and the reason I'm going to point these out, these 2 gamma genes aren't present in mice. Mice have all the other beta globin genes and all the other alpha globin genes, but they don't have, this is primate specific. And they're a real key. That's going to be the focus of what we're talking about. Okay, so just if you want to know more about the evolutionary history, I won't test you on these details, but it's real, there's still a lot of, as more and more genomes are being sequenced, they're finding more and more things having to do with it. So this is the common ancestor of both the alpha and beta. And here's some of the timing. This is million years ago. And again, I've highlighted these 2. This is only on the primate lineage. Now the terminology is a little confusing. The gene is called HGB2. That's the gene illustrated by G gamma. Okay, now the developmental interest in this is with the globin genes, is that this is a classic case of very tight developmental gene regulation. Because the thing about these genes, okay, remember, globin has 2 alphas and 2 betas. But during development and into postnatal life, there's a different composition of beta and alpha. So there's an embryonic alpha, but now we've got the alpha globin genes up on the top and the beta globin genes on the bottom. So of the alpha globin genes, alpha, this one embryonic is expressed first, but it's on the, now this is human, embryonic up until the time of birth. So look at first at the black. So this is that first embryonic alpha globin. It's present real early in the embryo, put it in decline. So the other alpha goes up and stays up. So essentially through most of embryonic development and postnatally, the same 2 alpha globins are present in hemoglobin. Look at what's happening. Look at the color coding here. Ignore the pseudogene. Embryonic, green, fetal, the 2 fetal globin, fetal hemoglobin. and to adult. We start out with the embryonic, that goes down in conjunction with the alpha, but then we get fetal. There's a switch. This is the globin switch between expression of the embryonic globin switching to expression of the fetal through most of the rest of the gestation. And it's also accompanied with, you don't have to know the details of this, but this switching is in part because the hematopoietic stem cells, the precursors to all blood cells, switch in their locations from the yolk sac, which is kind of the structure that comes around the embryo. The fetal liver, about mid-gestation, is where all of the blood cells are being produced. It's in the fetal liver. But late in gestation, it switches to the spleen and bone marrow, so that by the time of birth and after birth, it's almost exclusively in the bone marrow under normal conditions. But again, we get the switch between fetal being high, and that's almost exclusively in the liver, but then it goes down, the switches to around the time of birth, almost all of the hemoglobin has the two beta globin and the two adult beta globins and the two alpha globins. So why do we have these switches? Well, it's very clear. Now there are subtle amino acid differences between each of the different globins. Okay? And there is slight difference in oxygen carrying capacity. Now why would that be different between early in the embryo, mid to late gestation, and postnatally? Why would there be any difference in hemoglobin function? Yeah.
Fetus has some blood from mother.
Yeah, there's all kinds of differences in terms of the oxygen demand and accessibility in the fetus. And the fetus doesn't have, late in gestation, it's going to have all the lungs that are developing, but they're certainly not breathing air until after it's born. It was born, right? But this is the really interesting thing. Okay, we can explain embryonic versus adult. Fetal versus adult isn't so clear, especially since you can be virtually defective of any beta globin as long as you have what's called hereditary persistence of fetal hemoglobin, HeFH. That fetal globin perfectly compensates for any deficiencies in beta globin. That's the beauty of this thing. And sickle cell, mutated in beta globin, the other thalassemias are also affecting beta globin. People that have the normal switch and shut off their fetal globin expression have bad symptoms. Natural genetic variation exists. So some people, because of alleles that they inherit, have persistent expression of fetal hemoglobin, and their symptoms are virtually gone away. So that's where the gene therapy is coming in. Try to recapitulate what happens with the natural genetic variation. Try to find something that will allow us to control the levels of fetal hemoglobin. We don't have to correct the mutation that's causing the disease in beta globin. We increase the level of expression of something that will compensate for that. And that's where you can look at the rest of the slides and in the introduction to the design paper. That's where they took advantage of the genetic variation. Kaijon referred to a GWAS a couple months ago that looked for loci that are associated with higher levels of fetal hemoglobin. Now that was done in people that didn't have any disease symptoms. It's natural variation. You can't tell just looking at somebody or seeing how they function if they have higher levels. But they identified loci that controlled that. One of those loci is called BCL11A, and then through a series of experiments done, it clearly showed that BCL11A is a negative regulator of HPFH, of gamma globin expression. So if you've got, normally BCLA is what's responsible, major part of responsible for shutting down this expression. So if you want to have increased expression of fetal globin, would you want to knock down or increase the functioning of the regulator, BCL11A? Yep. That's exactly what the gene therapy is doing. I'm gonna just go ahead real quickly and say something. Did everybody vote? I can give you a lot of, okay, so that, I think, kind of showed you that very same G was, I show you a little bit and say, this is what's really remarkable. 2008, they got the first evidence that BCL11A was a negative regulator. Mouse model, BCL11A corrected the sickle cell disease in mice. More details about the mechanism. Look at the clinical trial. This is the knockdown of BCL11A that is resulting in
Because
effective gene
I
therapy.
really don't think I'll argue that much.
This strategy is not
Because I
going to
mean,
work
like,
in the countries
like
that
you,
most need
and like
gene
I think a lot of
therapy.
people have done
Or
that.
this
Tests are
disease.
not want to. At least I would.
Any questions?
I mean, at most you can do that.
Tuesday's our last day of class. Isn't it?
Are we writing our name?
No, it's enough. Do I want B or C? I don't know. I just think, since I know.
Do you not think she's also grading?
Oh, that's what I'm doing.
Let's see. Because I think I'd rather like prepare for that.
I added a couple of previews.